All right, we're going to introduce this new unit called atomic structure and periodicity. The main focus that we'll start off with, of course, will be the atomic structure. And one of the things I want to give you here is just an overview. I want to talk a little bit about light and exactly how light relates to the fundamental nature of matter. A little introduction to quantum mechanics. We'll talk about how we arrange electrons in an atom, and then we'll get into some of the history of the periodic table and some periodic trends, which refers to the periodicity that we'll cover later in this unit. But first, to start this, we're going to start off by talking about electromagnetic radiation, also known as light. So let's go ahead and look back at some material that we haven't talked about in a long time. Rutherford's model of the atom. Now, Ernest Rutherford, if you remember, he discovered the nucleus, or at least he provided evidence of the nucleus, and then further figured out that there's protons at the center of an atom. But one of the things that we have to remember is that there's just kind of this nebulous area around the nucleus that we just have some electrons around. How exactly are they arranged? That was a question that wasn't quite answered. And so that's something that we sought to understand following Rutherford's work. And so, looking back around the 1800s, sometime in that century, anyway, we made a lot of progress, but one thing we couldn't quite figure out is, again, how are electrons arranged around the nucleus? At this point, we just sort of know that it's just around. So this is what we sought to understand. And one of the first things that we have to recognize then is that, at least looking back now, is that we have to understand how light works. What exactly is light, and what are some of its behaviors that we can use to then somehow connect it to the atom? How exactly are light and the atom connected? So first of all, let's take a look at light as a wave. Now, the word wave, I think we understand, generally have, or at least have some understanding of it, but the technical definition is some sort of repeated motion through space, or again, getting a little bit more particular, the path of periodic oscillations through space over time. Now, oscillations refers to kind of this back and forth motion. So you can see here in this GIF that this point right here is going back and forth, and then as it travels through space, it generates a wave that comes out of it. And this happens periodically. It happens on a very repeated pattern over a period of time. Some other properties of light that we have to also understand is because we know that waves exist, right? Thinking outside of light, for example, we're talking about sound waves. We understand that waves have reflection properties, refraction, diffraction, and interference. So therefore, we knew that light also behaved as a wave. So just to kind of give you a visual again of what these four properties look like, we eventually made that connection to then say light also had these four properties, therefore light is a wave. So one, of course, is reflection, as, for example, we see here, as the light, again, bounces off a surface, it bounces away at an equal angle. And then refraction, which you also may be familiar with, especially the left side, is kind of the way that light passes through different media at different speeds. Therefore, coming out on the other side looks a little different. So you can see that on the left there, that's a refraction. On the right side, you can see that prism there. Again, there's a little bit of refraction that's involved to take white light, which then separates into all the different lights, different colors of light anyway. Diffraction, and this one's a little bit harder to maybe understand because it's kind of new, but basically diffraction is having light that passes through a small opening, or at least a wave that passes through a small opening and then fans outward. And that's kind of unique, again, saying that it doesn't go straight, right? So whatever gap you might see here, I'm going to kind of gesture at this, but you see right here, this gap, the wave that passes through doesn't continue to have just the width of that gap. Again, it fans outward. On the right side here, and this is one we'll talk about in a minute, but if you have two different gaps here, it actually generates a very unique pattern, but again, it all comes back down to this idea of diffraction. And then finally, the fourth characteristic is interference. And this fourth characteristic is basically a combination. So the word interference sounds like it's a negative thing. There really isn't that kind of connotation here. It's just simply saying two waves that interact with each other. So if you look over here, right, these two waves, the red line and the blue line, these two are going to be then combined. So when they combine, because you can see that these waves sort of are in lockstep with each other. As one goes up, the other one also goes up. When you combine these two, it makes this resulting wave right here, which is a combination again of these two lines down here. That's what we call constructive interference. But again, if you arrange the waves or orient them so that they are not in lockstep, as one goes up, for example, the other one might be going down, and then vice versa. As the red might be going down, the blue would be going up. When you combine these two waves together, you end up having something called destructive interference, where the two lines or the two waves effectively cancel each other out. And so again, this is just two examples of how interference works. Again, don't think of it necessarily as a negative thing, but simply just as a characteristic of how waves interact. So just a quick overview again of what we just went over. There are 4 properties of waves that we can acknowledge. That's reflection, refraction, diffraction, and interference. And the reason why we know that light is in fact a wave, or light behaves as waves, is because light, in our experience with it, also exhibit reflection, refraction, diffraction, and interference properties like other waves do. So let's also kind of break down parts of a wave here. So there's 6 terms here that some of which you might recognize, some of which are unfamiliar. But these again we'll be defining, and I'll be using the next slide here to sort of illustrate what those are. The first one is the origin. That's the central axis of a wave. So I'm going to scooch down here. That's going to be the central axis right here. That dotted line, that's going to be our origin. And then the next line says, or the next point here is the crest, and then the third one in comparison would be the trough. So the crest and the trough is the highest point of the wave, the trough is the lowest point of a wave. And so again, in the static image of a wave here, this would be an example of a crest, and this would be an example of a trough, right? The lowest point there, kind of a valley effectively. 2 other terms here, wavelength and frequency. These two are very often combined whenever you discuss them. The wavelength is the length of one repetition of a wave. So it's measured from crest to crest or trough to trough. Either way, it's wherever you see the repetition occur, that will be considered the wavelength. So let's go ahead and illustrate that here. So again, from here to here, right, this is a crest to another crest. That is the wavelength, right? And we'll label that wavelength. The other one is a little bit harder to visualize, or a little bit harder to illustrate with this static image, and that'll be frequency. So frequency is the number of repetitions of a wave per unit time. Now, for those of you who kind of imagine this, right, this wave that we're seeing on this next page here isn't exactly moving. It's not exactly easy to visualize time with a static image here. But if you can imagine this moving, right, going at a certain pace, that would be considered its frequency at this moment. And in a little bit, we'll see an example or two of what that might look like if you have different frequencies on a static image, but this is the best that we have for now. And then finally here we have the amplitude, this last term, the distance from the origin to a crest or trough, right? So we'll go ahead and mark that, meaning from here to here, right? This distance right here, that's our amplitude. Now that one is actually one that we won't see a whole lot of, we won't discuss very much, but again, you might see that in different contexts, and so that's why we mention it here. Wavelength and frequency, a couple of things you need to know about them. First of all, wavelength and frequency. These 2 things we'll use very frequently when we talk about light. So let's make sure we understand some of the basics here. First of all, wavelength. Wavelength, the symbol that we use to represent wavelength is lambda. So in the way that we represent mass with an M, or we represent moles with MOL, wavelength is represented with this lambda symbol. That's a Greek letter lambda, and you might want to practice writing it a few times. Kind of looks like that. All right, give yourself a chance to practice that so you know how to use it. And we'll be using this again in equations and formulas quite a bit, so let's make sure we know how to practice those. Units. Units are kind of variable here, but basically as a wavelength, it is literally a length, right? It's any length that you might imagine. But of course, it depends on the size and the scale, so sometimes you might see this meters, sometimes you might see nanometers, kilometers, and so on and so forth. So it just depends on the wave. Either way, the wavelength is an actual length. Frequency. Frequency, again, is the number of repetitions per unit time, but that's represented by this symbol right here. Looks like a little V, but in fact, it's the Greek letter nu, right, nu, and that's one that, you can stylize it a little bit. I like to stylize it in this way, but of course, practice it a little bit. Make sure it doesn't look like a V, right? We want to make sure that's not V. So again, the 2 Greek letters here you're learning, lambda, right, L-A-M-B-D-A, that's the first one, and this one is nu, that's just the simple N-U, right? That's the Greek letter nu. That should be a U. Units. Units are a little bit challenging here. Again, it's a repetitions per time, so it's a something per something. So there's a couple ways to look at it. Most often, you might see cycles per second. Right, second, of course, is the unit time. Cycles is the unit for repetition, but usually we simplify it down to either per s/s, s to the -1, or hertz, H-E-R-T-Z, hertz, which is abbreviated, or is the symbol of Hz. That's the units. So I might say that something has a frequency of 500 hertz, and you'll have to know that hertz also can mean s to the -1. These 2 are used interchangeably very frequently, so make sure you get familiar with that idea. So again, what's the point of discussing all of this? Well, let's go ahead and formalize this idea. Why do we talk about light? That's something we'll have to get to in a little bit, but we want to make sure we understand the electromagnetic spectrum. This word corresponds to light. What we use as light is a little bit casual. The real term for it is electromagnetic radiation. It's made up of two parts, electro and magnet, right? So those two parts, again, there's some interplay there that we're not really going to get into, but know that if you look at it, it's about there's an electron component and a electronic component, and a magnetic component. But effectively what we do is we have to acknowledge that there's a lot of different kinds of electromagnetic radiation. There's all sorts of them. So the entire range of them all together is collectively called the electromagnetic spectrum, right? The word spectrum I think you're familiar with. And so when we talk about light most of the time, right, it's a very casual word. Most of the time when we as human beings, normal human beings, on a day-to-day basis, we're really referring to visible light, which is that part of the entire spectrum, that whole spectrum which we can see. And that's a very, very tiny section. Here's a little illustration that I want to use to kind of mark up a few things. So this is actually a graphic that we'll use and reference quite a bit. And I want you to know that you'll have to know a lot of parts of this, but you won't have to memorize any of the numbers. You won't have to memorize exactly where things are in that sense. But you do have to get a sense of the relationship of the different types of light. First of all, let's go and orient ourselves. This middle section right here, right, this is going to be a section that sort of illustrates the wavelength and the frequency for us. So on the very far left over here, right, you can see that these waves are very spaced out. The crests are very far apart, whereas over here on the right side, these crests are actually really close to each other, so the wavelengths are a lot shorter. So the language we use here is longer wavelength, and of course remember wavelength we represent with the Greek letter lambda. And then over here on the right side, we have shorter lambda, shorter wavelengths, right? So the distance between the crests are a lot shorter. On the other hand, if you can imagine this being a moving wave, right, as it goes back and forth and moves through space here, we actually, again, would talk about frequency. As see over here, right, it looks like this wouldn't repeat as frequently. So what we say is that this one has lower frequency, right, which means, again, or is represented by the lambda, or the nu, excuse me. And over here, we say it's considered to have higher frequency. So these two, again, you can see as a relationship to each other. The longer the wavelength, the lower the frequency, right? Meaning the longer these take to repeat themselves, the less frequently they repeat. Right? And then on the right side, you have shorter lambdas, shorter wavelengths, which means they repeat much more frequently. So these two, again, are in a nice relationship with each other. All right, a couple of things to orient yourself with here. You see right here that there's a wavelength up here, and these represent the actual wavelength markers. So this would be something that has a wavelength of around 10 to the third power, whereas down here we have a wavelength that's around 10 to the minus 12th, which again is corresponds well to the longer wavelengths that we delineated over there, and shorter wavelength we have for here. Same thing with the frequency. Frequency is using hertz as its unit. 10 to the 4th power on the left side, 10 to the 20th power. So again, low frequencies, high frequencies. And this section right here, if you notice again, most of this is dark, right? Most of this is black. And then this section here in the middle has some colors. And this section right here is that visible spectrum that you probably recognize. But this little bar on the bottom here, you can kind of see here, these are, again, the rainbow's colors, and they all, again, are just squished into this little section. They've expanded out this part right here. So, again, don't think that this red corresponds to this. Right? That's not the case. Or that the purple corresponds to that. That's not the case. All right? Again, all of this is squeezed into, really, this section right here. So each of these sections, again, if you notice there's little numbers, these kind of correspond to each other. So 10 to the 3rd of for your wavelength kind of corresponds to 10 to the 4th of your frequency of hertz. Whereas over here, 10 to the minus 12th meters, right, that kind of corresponds to 10 to the 20th hertz for frequency. So there's a little bit of a sort of a matchup there. It's not perfect, but it's a general line up there. And then finally, what I'm going to do is go ahead and walk you through this and make sure you know that each part kind of has a very specific type of electromagnetic radiation. So this is the entire spectrum on the very far left. Actually, let's do this in the middle, right? This section right here where we kind of see these colors. This section right here lines up to being your visible spectrum. Right? That's your visible spectrum, kind of in this range around here. Now, if you look to the visible spectrum, you know that going to goes Roy G. Biv, right? You remember that that saying of red, orange, yellow, green, indigo, blue, indigo, violet. So that's going to be Roy G. Biv, whatever indigo is. And that spectrum, again, covers that bottom. to the left of it, right, if I know that Roy G. Biv red is kind of over here, right, and violet's over here. So if I go to the left, this actually ends up corresponding to infrared. Right? I'll abbreviate a lot of times as IR, but that's spelled INFRA, red, infrared. To the left of that, and we see over here, we have microwaves. I mean, that same microwaves, at least that same term anyway, for that thing that zaps your food and makes it hot within minutes. Keep going to the left of that, we usually over here see radar/radio waves. Right? The distinction there is not super important and not very delineated, but again, it's still there. To the right of that, right, we have the violet on the visible spectrum. So if we go past it, right, some of you can kind of see where this is going. This will be your ultraviolet. Right, I'm just going to abbreviate it UV because I don't feel like spelling that out, but you get the idea of how to maybe spell that. Ultraviolet. One more step past that, right, getting to shorter and shorter wavelengths, higher frequencies, we have X-rays. Right, you've probably heard of that before. And we keep going past that, and we have something called gamma rays. Right, gamma is also another Greek letter. If you're interested, gamma kind of looks like that. That's your gamma rays. Right, that's effectively your electromagnetic spectrum and how it breaks down. So be sure to be familiar with this and know how it's oriented and what's high, what's low. And to finally finish it off here, let's talk real quick about this wavelength versus frequency. All right, so you can see that, for any ray of electromagnetic radiation, so any ray of light, effectively, the frequency and the wavelength are inversely related. So the product is equal to a constant. We see here, lambda times nu is equal to c. Right? Well, c you may have heard of, but c actually represents the speed of light. Right? And so any ray of light has a certain speed to it. It's always the same. It's always going to be 3 times 10 to the 8th meters per second. Right? You can go ahead and commit that to memory. And as you can imagine, we're doing calculations with it. So in terms of significant figures, this is a constant. Right? So that's going to have infinite sig figs. And again, as you can see here on the right side, right, we have a couple of examples here where you see the wavelength, and you can see that there's a certain frequency where this is 1 second, right? So this thing repeats itself about 4 times. And down here, within that same 1 second, the second wave right here, right, that frequency is much higher. It repeats itself about 8, 9 times. And then on the bottom here, lots of times, that's going to be 16 times it repeats itself per that same unit of time per second. So you can see that wavelength and frequency are inversely related because up here, the wavelength is longer, it gets shorter and shorter. Frequency is pretty low here and it gets higher and higher. So they're inversely related, and they can show that relationship by using the formula of lambda nu is equal to c. All right, that'll do it.